Page 11 is not just any old page. Page 11 and 12 is actually the checkup in this pace. So let's look at these sections together. We'll do some of them. On page 11, starting with number 5, our directions there say, write the ratio of the first number to the second number as a fraction in lowest terms. We learned this right at the start of the pace, so I'm sure you'll be able to do these rather quickly, but it's the lowest terms part that you don't want to miss. So of course your first one, number 5, is 81 over 162, but what does that reduce down to? 162 and 81. The clue is 2 times 1 is 2, 2 times 8 is 16. So what do you reduce that fraction to? 1/2. That's right. Next one is 13 and 5. So you put the 13 up top, 5 in the bottom. As far as the lowest terms go, that's it. Same with number 7. You have 6 and 47. So you write 6 over 47. And then number 8, 125 over 25. And now that one we can reduce. Lowest terms makes it become 5 over 1. Next section. Yes or no?
No.
Can these ratios be set in a proportion? There was a particular clue you're looking for. You may notice, multiplying and it becomes the same, but also there is the cross multiplication. Our very first theorem in the pace is the product of the extremes equals the product of the means. Are you able to keep straight which is the means and which is the extremes? It isn't necessarily easy to remember, but you definitely know that that means cross multiplication. You multiply across and they should be equal. So that means that's a great test for this section. If you look at number 9, you see 2 over 3 and 10 over 15. So 2 over 3 and 10 over 15. Could that be set as a proportion? In other words, could you write an equals in between, that these would be a proportion? One test is 2 times 15. 2 times 15 is, in fact, 30. And 3 times 10. 3 times 10, 30. Since the product of the extremes equals the product of the means, then this is a proportion, and you would write yes for number 9. Let's jump over to number 14. 1 over 5, 1 over 50. Would this rule apply to 1 over 5, 1 over 50? You would have 1 times 50 equals 1 times 5, and we know that that is not true, since that would be a no on that one. What about number 15, though? 11 over 2, 33 over 6. 11 over 2, 33 over 6. 11 times 6 is 66. And 2 times 3, 3, is 66. That one checks out. So number 15, that's problem number 15, is a yes. One more. Problem number 16. 12 over 5, 48 over 20. Problem number 16. What did I say? 12 over 5 and 48 over 20? Okay. Got to get your writing math out skill or calculator skill here may be involved. And what is 5 times 48? Someone, anyone? 240. 5 times 48? 240. And what about 12 times 20? We see 12 times 20 would be 240.
Good job, Yippee.
Works, so 16 is a yes. So those are the first two sections on the checkup. You're writing ratios, and then you're determining, hey, could these be a proportion or are they not? So you're putting yes and no. The next section, 19 through 26, is finding values for x in proportions. Now you're being given a proportion, so you already know that these are written for you. So the answer to these, are they a proportion? Yeah, these are all proportions. Now we just need to know, how do I solve for the missing piece? What's the missing piece? X over 4 equals 5 over 20. What's the simplest way to solve this proportion? Using our cross multiplication. The product of the extremes equals the product of the means. And then we write it down. 20x equals 4 times 5. Wait a minute. 4 times 5 is what? 20. So 20x equals 20, and I would divide both sides by 20. Then I would find that 20 divided by 20 is 1. So x is equal to 1 there. That's what you write in your blank. Jump down to 22. 10 over 13 equals x over 52. 10 over 13 equals x over 52. Now, since this is a proportion, my unknown can be anywhere. Answers? Well, we start with our cross multiply. What's 10 times 52, do you suppose? 520. Now we need to divide both sides by 13. So x is what? 520 divided by 13, what do you get? Write that down. You might find out that it equals 40. Look at the next column though. So that left-hand column, very simple. And then what did they change in the right-hand column to make the problem just a little more complex? A little bit. X plus 3 over 5. And what does that set equal to? 2 over 1. So it's not just an x anymore, x plus 3. Should I still follow the same steps and cross multiply? What's x plus 3 times 1? Well, that's just going to be x plus 3 equals, and then 5 times 2, 5 times 2 is 10. So if x plus 3 equals 10, now I know what to do. This is a simple algebra problem. I need to get x by itself, so I would subtract 3 from both sides, and I have x is equal to 7. These are the same. The only thing that's slightly different is number 26. That looks like it's even more complex. I see some variables all over the place. You think that one's possible to do? X minus 2 over 3 is equal to what? What's the next side? X plus 4 over 5. Wait, can I have unknowns like that? I thought I just needed to have one unknown. Well, how many unknowns do I have in this proportion? It's kind of a trick question. It looks like 2, but there's really just one variable. So, x minus 2 times 5. Now, that's probably not the most ideal way to write that. How would we normally write it? 3 times x plus 4, like here. So normally I would put the 5 out front and not back there. That's just sort of the way we would normally write an algebra equation. I go ahead and finish this out. 5x minus 10 equals 3x plus 12. Continue solving for x. What do I want to do? Get this over here. So add 10 to both sides. What does that give me? 5x equals 3x plus 22. I'm never going to edit out all that tapping.
I can't pick up that much tapping.
Minus 3x what's left? 5 minus 3, 2x equals 22. Look how nice.
Looks like a mad face.
Divide both sides by 2, and I find that x is equal to 11. So what looked like was going to be challenging, a couple extra steps, but we got there. No problem. That's the page, the left side of what we're working on now, page 11. Well, really right side of the page. So that was page 11. Now we get to move on to the next page, page 12. On page 12, what do we find? The second half of the checkup. Problem 27 at the top, so number 27. That asks us to find unknown lengths in that triangle. So I've got a triangle that looks like this. X up here, R here, Y there, S here, and Z. This is the triangle that's drawn for problems 27 and 28. We're given some lengths, and we're supposed to find the unknown. For problem 27, what we're supposed to find is this here. That is our X length that we don't know. Now, setting it equal to X might be a little confusing because you have an X as one of your points labeled, but don't let it confuse you. That's where my X is for number 27. I'm also given the length of SZ. That's here, that's 10. And I'm given the length of RY right here, that's 6. And I'm given XR at 9. So how would I set that up as a proportion? I'm solving for proportions. How would I set that up as a proportion? Well, it is sort of laid out there for me. I could just use what's written on the board and put 9 over 6 and set that equal to X over 10. Are there other ways to write that? Sure. I could flip this around, as long as I'm following the rules of proportions. If I solve for X now, I get 6X equals 90. Divide both sides by 6. Does X equal, or does 6 go into 90 evenly? 6 goes into 9 one time. I'll be left with 30. 6 times what? We're dividing.
Yeah.
90 divided 6. Do we need to write it out? 6 goes into 9 one time. 1 times 6 is 6. Subtract that and left with 30. 6 goes into 35 times. 5 times 6 is 30. Subtract that and left with 0. 15 is my answer. Right? Long division. You have a cheetah that you can use to help find that should you have trouble. So the answer is not 1, but 15. My unknown length here, x is 15. That's what I found. Does that appear to make sense, though? You've got an answer. Now we want to look at our drawing just briefly and see, does it make sense what I did? This is bigger than that. It would make sense that this would be bigger than that. That seems like that would be proportionate. And if we were to put our 15 back in up here, does that look like a proportion? Yeah, because we know that 6 times 15 is equal to 90. So it works. Now we have some new links to look at in problem 28. For number 28, I'm told RY is now tinier. 2, maybe we're zooming in. SZ is now 6. XS is now 9. And this one is now my unknown. Oh, how would I set this up? What would you do? Maybe do like we did before. X over 2 equals 9 over 6. So I have 6x equals 18, because I'm cross multiplying using theorem 84. And I see that x here would be 3. Does that make sense? Hopefully so. Number 29. It says, using theorem 85, write 3 equivalent forms of these proportions. Now that's the theorem that we're really referring to when I say how should we set up this proportion. There are equivalent proportions that theorem 85 gives us. What all are they? Go ahead and work on those. Tell me what you get. 29 is 6 over 9 equals 2 over 3. Based on what theorem 85 tells us, because of the different ways you can rewrite this problem, what's another way to write this? That's a big comma. What do you got? I can switch these two, right? Making it 6 over 2 equals 9 over 3. And there's a couple other ways you can write that. You can write 9 over 6 equals 3 over 2. And there's one more. So you can finish practicing that for 29. 30 is the same thing. You're writing equivalent forms of the proportions using theorem 85. Theorem 86. These are interesting. Look at what happens here. We're now on problem number 31. Number 31 says, use theorem 86 to write a new proportion by addition. Look at this. I have 3 over 4 equal to 15 over 20. That is a proportion. The addition piece of theorem 86 tells me that I can add the denominator to the numerator and it still remains a proportion. Does that feel like that should work? Let's see. Let's just test it. 3 plus 4, 4's from here, so I still have my same denominator, equals 15 plus 20. I got 20 from there. If I were to finish this, 3 plus 4 is 7 over 4 equals, and this is 35 over 20. And look at that. Still a proportion. Still passes the test. You can also do this with subtraction, which is what we are doing with 33, 34. So that's problem number 31 and 32. Uses theorem 86 for addition. It says it also works with subtraction. Let's test that and see. Now, problem number 33. 5 over 2 equals 15 over 6. So I'm putting my denominator, subtracting it from the numerator. 5 over 2 equals 15 minus 6 over 6. This is 3 over 2 equals, and then what's 15 minus 6? 9 over 6. And when you know, still a proportion. So it does work, theorem 86. Any questions about that so far? Still on page 12 here, let's look at number 35. You will see that you have what appears to be a square and what appears to be a rectangle. So we're supposed to indicate whether these polygons are similar. Now a square and a rectangle would never be similar, but we're supposed to just look at the numbers, because the shape for 36 is not nearly as obvious. All right, our question is, write yes or no to indicate which polygons are similar. If it's yes, you're going to give your reason why you think it is. Same as if you would the same when you say no. You got to give your reason. So number 35, we're going to say no. But why? Well, the sides are all 8 all the way around on that square. And this remains 8, but these go to 16. So our sides, we would say no, not similar polygons. The y is the sides are not what? The sides are not proportional. If I set this up as a proportion, 8 over 16, for example, and then I chose this side to do next, equals 8 over 8, doesn't work, not proportion. Since that's not a proportion, these are not similar polygons. So that's the test you would use. Now this was a little bit more of a simple example, but a great starter to make sure that you can see what you're doing and why. What do you think about 36, yes or no? And whatever you say, what's your answer? What's your reason why? Anyone?
Yes.
We got a yes. All right. We moved on to 36.
You just picked a random question to skip on the checkup.
What?
Oh, hold on. Never mind. Take it back. Hey, yo.
It doesn't exist. I was looking for it. It's like,
Yeah,
it doesn't exist.
What doesn't exist?
number 13 on page 10.
Yeah. No, I looked at number 10 on page 13 and didn't find that either. So I was just like, alright, I'm done. We're not skipping anything.
I was like, what?
It's on the
What happened?
goal sheet on the first page of it for today's goals. But skip a certain bit and it's not there.
Well, it certainly is. I see it.
On page 10?
Yeah, it's right there.
You made a mistake.
I'll have to look into my assistant and see what's going on.
Maybe it was 6 and 7.
I started getting confused. I was looking at it, I was like,
You're talking about yesterday's work?
oh, it says today.
Well, but we don't do page 10 today.
Yeah, but it says number 13 on page 10.
Yeah.
Are you sure?
Or is it page 13, number 10? There's no
Either
number.
way, I did this yesterday. It's the exact same thing happened.
The confusion that was on my face. I was like,
I saw you looking back and forth. Like, what are you doing?
I know, but I wanted you to feel like you had something you could skip. You know? Oh, yes.
like for real, I was like, wait.
Cruel and unusual punishment. I don't know. Maybe that had carried over from something else. Or, I think maybe it's a different edition of the pace. How about that? We'll go with that. Where were we? Number 36, we've got a yes, but we don't have a reason.
Somewhere.
Number 36 on page 12. We have a yes. What would you say is the reason? If you look at your two polygons, you'll see that the shapes do appear to be similar. So you start to match up and you realize that all of the angles are congruent. All of them. The corresponding angles, that is. And the sides are in fact proportional. You could set up a proportion, pick two sides and set it up and you'll see that they are. So that your reason is the corresponding angles are congruent and the sides are proportional. Number 37. 37 and 38 want us to find unknown lengths if polygon ABCD is similar to polygon WXYZ. You can do that because you can set up a proportion and get the two answers. So you should be able to do that without too much difficulty. Let's look at our next couple of pages for today. Now, we're learning a couple of new postulates, but they are very similar to each other. Postulate number 29. Plus, we get to go to triangles. What are the greatest shapes? Triangles.
No, they're not.
Up to this point, the only way we have established to prove triangles are similar.
Squares. Squares are the best.
You're reading the top. There are several other ways. If two triangles have corresponding angles and the lengths of the corresponding sides are proportional, then those triangles are similar. However, we have more things we can do. Postulate 29 is called the angle similarity postulate. This reminds me of when they were naming batteries. Where's the A battery? Where'd that one go? We have a double A. And then we made one smaller, and we called that, here we have A, don't have.
Why?
We have A, and ah!
Yeah, what happened to what happened to just A?
So we don't have this battery anymore, just these two.
It just died.
Imagine what this battery would look like.
Oh, it'd be so precious.
Like a tiny little one. All that 1.5 volts crammed in there.
I remember, I think it was you. We had an argument in physical science class that nothing can be started with one battery. Like a flashlight.
What?
We had an argument one time, like a flashlight. He said there's no flashlight out there that starts with only one battery. everything takes at least 2 batteries of something. I found a flashlight.
How long does it last?
I have no idea.
I mean, you're not getting very much volts out of that, so it wouldn't be a very bright flashlight, I wouldn't imagine. But hey, you know, maybe you want a unusually dim flashlight.
It's better, you know, like those little toys, like the ones that sing, you can change the color. I used that one time as a flashlight through Alma's house. I couldn't find a flashlight.
So our angle, similarity, postulate. Postulate 29. It says if the angles, or you might even think about if all the angles of one triangle are congruent to the angles of another triangle, then the triangles are similar. And they give you a drawing here of 2 triangles, and then they've labeled them, and then they've also marked the angles as congruent, showing you that in fact all 3 angles are congruent. And then you look at a proof below it. And guess what? We made it. We have 2 triangles that are drawn there for you, triangle ABC and DEF. It's a very simple proof, 3 steps. The first one is given, that triangle ABC is congruent to triangle DEF. Do you see that? Your job is to prove, are they similar? So are congruent triangles similar? Well, we know that our last step is to say they are in fact similar. And this is on page 13 with postulate 29, so we realize we're probably going to use the angle similarity postulate as our reason number 3. Oh, but what is step number 2 in the reason, do you suppose? Well, look back at postulate 29. It says if the angles of one triangle are congruent to the angles of another, and we've been told these 2 triangles are congruent, what do we remember? That is our glowing orb tool that we can pull out of our tool bag when we know that 2 triangles are congruent. You would be able to say that angle A is congruent to angle D, angle B congruent to angle E, and angle C congruent to angle F because of CPCTC.
Wow.
So that's your reason number 2. All right, now let's look at theorem 87 and just see how different they are from postulate 29. If 2 angles of one triangle are congruent to 2 angles of another triangle, then the triangles are similar. I felt like postulate 29 said if all the angles are congruent to another triangle, then they're similar. This one says if only 2 are congruent to 2 angles of another triangle, then those triangles are similar. So we eliminated one angle. But we know that's just fine.
The poor trio. There's always the one left out.
If you recall, some time ago we learned theorem 19, corollary 3. If 2 angles of one triangle are congruent to 2 angles of another triangle, then the remaining angles are congruent. And if that's true, so if any 2 angles in a triangle are congruent to 2 other angles, theorem 19, corollary 3, tells us that third angle is also congruent, then you go right back to using the angle similarity postulate. So that's how you prove theorem 87. Theorem 87 is more useful because you know less information about the triangle but can still prove similar. That's pretty valuable, right? You don't have to go to the trouble of proving all 3 angles within a triangle. So now we get to practice. This is good practice. You want some good practice for knowing how to prepare for something you might see in the future? Boom, bottom of page 14.
I will see it once in my future, and besides that, never again.
Oh, many times in your future. Imagine the number of times you'll encounter this dilemma. How will I ever know if those 2 triangles are similar or not?
Where am
I
gonna be
know.
seeing that?
I mean, it could happen in life somewhere. You might just be out and about, roaming around, walking the streets. There's that problem.
But
Other people will struggle, but not you,
Yes, I will.
because you'll have the answer.
You'll be trying to remember.
Like,
What's Theorem 87 again? I know this would be helpful in the situation. It would be interesting if that's how you had to arrive at information. You go to the airport, you're trying to look at what time your flight arrives. Instead, it's a geometry problem. As soon as you solve it, you know the answer.
oh my goodness. Like, what if, like, that's how, like, you figured out, like, the speed limit or something? Like, you had to do, like, you just drive by, like,
Every time you drove past, it's presenting you with like a square root times something divided by this. You're like, oh.
let's slow down just a little bit.
And each one's different, as you
know
go
what
along.
speed limit is, sir? No.
I left my calculator at home. Pretty soon, though, you'll have AI systems in your car. You can just ask it.
True.
So then they'll have to take those signs down and put up something more complex. I don't know.
Find the traffic lights.
All right. Next. Number 3. Yes or no to indicate if these triangles are similar. And you have to use the angle-angle similarity theorem. That's Theorem 87. And then you would need to write down how many pairs of angles we know are congruent. That's sort of an afterthought, because if you have 2, then it's going to be a yes based on what Theorem 87 tells you. So according to number 3, would that be a yes or no? The triangle looks like this, and they've marked those 2 angles. So we're comparing this triangle with that triangle, right? Are these 2 triangles similar?
Sure.
It looks like they've only given you one angle as similar, though. Is there a second angle? So if you can write 2 in the blank, the answer is going to be yes. But is there a second angle that's congruent? I got this one. I don't know anything about that one. What about that one? That one I can mark because this angle is shared by both triangles. So that is in fact a yes, and it's 2 angles that I know are congruent. For number 4, they've drawn 2 triangles side by side. They sure do look similar. And in fact, they marked that one angle. And then they gave you lengths of the sides. Even though those lengths of those sides are proportional, does that help us determine if these triangles are similar using the angle-angle theorem 87? No, it doesn't help. So you're going to have to put a no there because you only know that one angle. So that is what you're doing with those problems on the bottom of page 14. Thankfully, we saved a little bit of time by skipping number 13 on page 10. So we've got a little extra time in class today. Look at that. 1 minute to go. Which is probably worth pointing out what's on the next couple of pages, because tomorrow you're supposed to do page 15 through 18.
You saying that?
Now 9 and 10 don't really look like proofs because there's no reasons you have to give. But in order to fill those problems out and solve, you're basically working it like a proof. So let's give you a little tip what you need to do with number 10. Number 10 has triangles drawn on top of each other. Now, what do I always recommend when you have a problem like that where the triangles are drawn inside each other or on top of one another is separate them out. Draw them separately. So that means draw it out where you have A, B, and C, and they wrote 90 there for you. And ADE is right inside here, and they've drawn a right angle symbol. Now I'm not even going to bother drawing it there because I want to take and redraw that triangle over here. So the right angle one is D. This is E, and that's A.
Oh, you hit it.
This A is the same A. What happened?
You accidentally hit the
I've
arrow.
been like tapping my foot against the tripod for like a few minutes now.
I accidentally started doing that
I
too.
was like, wait, what's there? I started thinking like there's not a table leg there, and I was like, oh crap.
So A is similar, or A is the same angle, not similar. A is the same angle. If I took this triangle here and I were to pick it up, flip it around, and stick it right there, right? That's where this came from. You see that in your drawing? So I recommend highly that you draw these out separately when you've got a complex problem like that to do. The rest of those look like geometry bow ties, and we always know what one of our favorite things to use when we have a geometry bow tie, when we're dealing with congruent things, right? Is what? Reflexive. So you probably use that in your thinking. What I would say, though, when you're talking about geometry bow tie, is not reflexive, though. Reflexive applies more to the paper airplane. So if I have this, that is reflexive, remember? But this is what?
Oh.
Vertical angle.
Yep, that one.
Vertical angles congruent, right? So that's what you use when you're dealing with the geometry bow tie. Vertical angles congruent, which also happens to look a lot like maybe Spider-Man or something. So
No, that was the other one.
yeah, well, this, because I circled it. So reflexive when you have a paper airplane, vertical angles when you've got a bow tie.